For those of you who haven't met him, this is Reggie Taylor. He's our main head MR physicist in the VIC and the IMHR. He is your go-to guy, especially for any MR questions, but he's got lots of background in tech. So anything you need protocol development-wise, you can go to Reggie. We still also have Greg and Garrett available for kind of specific things that maybe is their focus area, or if they've been helping you develop your project so far. But Reggie's kind of our guy on site now, which is awesome. So Reggie did his undergrad and his PhD in Medical Biophysics at the University of Western Ontario, and he stayed on there to do his postdoc as well at Lawson Imaging on their Siemens Biograph PET MR, which is exactly the scanner we have here. So he's got quite a bit of experience with that scanner as well, and he's going to give us some ideas for getting MR sequences onto our scanner or the scanner that you have at your site if you're not using ours. And I'll let him take it away.
Okay, thank you for the introduction. So I know the title of the talk says bringing state-of-the-art sequences onto your MRI. I will talk about that, but I figure a lot of you don't know me, so that's only going to take like 15 minutes to really talk about that. So let's figure I spend the first 10-15 minutes giving you an introduction to who I am, some of the work that I've done, some of my past research, just so you get a feel for where my specialties lie, and if you ever want to have any questions or want any help on future projects or collaborations, just let me know. So just a quick outline. I'm going to briefly discuss my career role. Katie just mostly mentioned all that. No, it's fine. I have half a slide to it. So, and then talk about my past research, my PhD, and my postdoc. Again, just very briefly. I'm going to touch over a lot of projects, just kind of like a sentence or two about a lot of them. So if you find that I lose you for a second, just kind of hang in there, and they'll probably be onto a new topic in a few slides. So. And then, yeah, I'll get into the main point of the talk in the second round. So yeah, again, this is my only slide on the topic. I'm the on-site physicist working on the PET MRI. I'm available as a resource for any PET MRI related questions, any protocol development, any pulse sequence development. I'm happy to help. And also, if you have any questions about analysis of the data, particularly when it comes to programming, that's something I'd be happy to help with. So yeah, I'll first mention my PhD and then on to the postdoc. My PhD, this was the thesis behind it was essentially using functional MRS, so spectroscopy, in schizophrenia and major depressive disorder using 7 Tesla. It was divided into 4 chapters, so we did some simulations just to validate our work. We did single voxel spectroscopy in the anterior cingulate and the thalamus and schizophrenia and major depressive disorder at 7 Tesla. And then, yeah, the goal was to do functional spectroscopy, so we have a study just in healthy controls, just as a proof of concept technique, paper, I guess. And then we extended that to schizophrenia and major depressive disorder. I'm going to skip over these simulations because they're very boring, so I won't waste your time with that. This is the sequence, or sort of the scanner that we use. It's 7 Tesla head-only system, so you can see they actually dug into the ground here. It's actually a lot bigger than it looks, because they elevated it a little bit. And that was entirely to so the volunteers wouldn't feel as intimidated, because they were going to have to be risen up a long way and then put into the scanner. So just to make it a little easier on them, they raised up the platform there. It was originally a Varian system, and Varian got bought by Agilent. And then Agilent decided not to keep working with the system, so they kind of hung us out to dry, and now it's a Siemens system. But most of my work was done when it was a Varian system. So you guys are very lucky to be working with Siemens systems here, because there's so many people using Siemens systems that if you have any questions, or if you want any sequences, there's tons of people working on it, so you have lots of resources. And this is the sequence that I spent most of my time developing. It's based off of a sequence in Minnesota. I don't expect you to follow any of this. The top line is the RF waves you're sending, and then the bottom 3 are the 3 different gradient axes. I just put that up there so you can know, or so you can see that when you're requesting a new sequence, it could just be the addition of one extra articles or a couple different gradient patterns in there that can make all the difference in your sequence. So it's important to know that there's tons out there. Yeah. And so this is a version of the STEAM sequence. So on your system, every Siemens platform has a STEAM sequence, but this is one that we made a bunch of modifications to, and it's way better than what you get on the system. And just because I spent so much time doing spectroscopy, I've kind of talked about it a lot there, just figured I'd give you a brief introduction on what spectroscopy is. So in a very simplified way. So if you take an MRI image and you look at a voxel in there, you're looking at the intensity map of water in that voxel from the 2 hydrogens from H2O. But in reality, there's actually contributions from every proton that are about 50,000 times less in concentration. So you don't see it in the voxel. It's not a meaningful contribution. But these, so this is glutamate, glutamine. You would have contributions from these 2 hydrogens, these 2, and then this one. You don't really see these because they exchange so quickly, but they have different local magnetic fields, gives you different electron environments. So they actually resonate at a slightly different frequency, and you can use that to your advantage by, if you can suppress the water, just completely get rid of all the water, you're left with all these different spectral signatures of other metabolites that can give you meaningful information of the health of the tissue. So this is one of the spectra that I acquired. You have NAA, glutamate, glutamine, creatine, choline, minoxidil, and glycine. And like this is all that's left of the water here, just that tiny little peak. So you can very effectively get rid of that and then measure these concentrations. Originally, we were just interested in glutamate and glutamine, but in the end, we actually got some very interesting results in glycine and minoxidil as well. So we wanted to acquire, you can't really see the yellow on there a little bit. We wanted to acquire these spectra in the anterior cingulate and the thalamus in people with schizophrenia and major depressive disorder. So again, you can see them there, anterior cingulate and thalamus. And some of these results I found were very interesting. In the anterior cingulate and the thalamus, it's kind of a tough graph to read, and the laser pointer isn't working, unfortunately. But we saw consistently decreased myoinositol in the major depressive disorder group relative to the healthy control and schizophrenic group. And the reason why I find that interesting is because in bipolar, there's one of the treatments is lithium to reduce mania. And one of the ways that works is it acts on reducing myoinositol. So myoinositol, it's kind of a catch-all metabolite. Like it's involved in a ton of functions. It's a big osmolyte. But this is in major depressive disorder. It's very it hasn't been studied a whole lot. There's only a few groups that have shown anything using spectroscopy that they have decreased myoinositol. So if you're doing any studies on major depressive disorder, I may be trying to piggyback an extra scan or two onto your study to look into this a little bit more. And then the other big result that I thought was really interesting was we saw significantly increased glutamine in schizophrenia relative to the healthy controls, and significantly decreased glycine in schizophrenia relative to the healthy controls and the major depressive disorder group. And the reason why that is so interesting is because this is the glutamate-glutamine cycle, and one of the big hypotheses in schizophrenia is that it's the NMDA hypothesis, that it's in a state of hypofunction. So that the NMDA receptor isn't working quite so well, and it's inhibiting this whole cycle. So if you don't have enough glycine, then the glycine is an agonist to the NMDA receptor, so it's going to be in a constant state of hypofunction. And I didn't include any of the stuff that's happening down here, but when it's in a state of hypofunction, it actually comes back and acts on glutamine synthase right here to increase your glutamine. And both of our results in glycine and glutamine are consistent with that. So I thought that was very interesting. So again, if you're doing any studies in schizophrenia, I may be trying to piggyback an extra scan on there. And then we ultimately wanted to do functional spectroscopy. So just as proof of concept, we did that in healthy controls. We used a modified Stroop task. There were 4 conditions. The first one was congruent, where they match up. Incongruent, where the word and color don't match up. Color only and word only. In all these examples here, the answer would be red. We would give them 2 seconds to respond. And it did a very good job of activating the anterior cingulate, which was the point of this kind of proof of concept study. And our hypothesis was that we would see increased glutamate based on what other people have shown in the visual cortex and the motor cortex. And we did see that. It's kind of hard to see the block there, but it was a 4-minute region of activation. And yeah, we saw increased glutamate. So we were happy about that, so we extended it to schizophrenia and major depressive disorder. And we replicated our first study very nicely. In the healthy controls, we saw a significant increase in 4 minutes of activation. And we added a second block because we were expecting it to go up and down and up and down again, but it didn't happen that way. We don't know why. My old supervisor has designed experiments to look into that, but it was an interesting result nonetheless. We didn't see any significant activations from the group of schizophrenia or major depressive disorder, but you do see there was an increase. It seemed like it was slower to develop. So why exactly that is, we don't know, but again, we're putting more experiments into figuring that out. One really interesting result was that there was a significant decrease in glutamate in the major depressive disorder group in the second run. Again, we don't know why. And one result that I don't have here on this graph is that there was a significant increase in glutamine in the first run of the task in the schizophrenic group only, which again is consistent with the NMDA hypofunction hypothesis. So a really interesting result, but that deserves more investigation, I think. And then on to my postdoc. It was a MyTax postdoc, so I had part of my time was spent at Lawson working on various projects on T MRI. This is pretty much the identical scanner to what you have here. And then the other half of my time was spent pulse programming with Siemens. Worked on a lot of different projects. I'm not going to get into all of them, just briefly mention them. I was modifying a cardiac sequence to add a saturation pulse that would clean up the B1 inhomogeneities. We were working on extending attenuation correction to the whole body. So there's it's very good at, the current methods are very good at correcting for attenuation in the skull, but we wanted to extend it to the whole body. So we actually worked with a guy that came over from Copenhagen on that. One project I spent a lot of time on was the spherical navigators, which was a motion correction technique, retrospective for PET and prospective for MR. Did some time doing coil evaluations with Sarah Senza, looking at their head coil and cardiac coil, and they developed some multi-nuclear coils as well. So I was testing those. I also did some pulse sequence programming for the multi-nuclear sequences. Another one we worked on was chemical exchange saturation transfer, which it's called CEST. And I'm not a fan of that technique, but yeah, they were interested in it, so we tried it out. It didn't really work that well at 3T, unfortunately. But probably the one I spent the most time on was using the PET MRI to look at prostate cancer. And what we did was we concurrently acquired PET images and MRI images. So we got PET data. So you see this really bright spot there. The tracer was 18F DCF2IL. It's a very specific tracer for prostate cancer, and if it's metastasized to anywhere in the body, it shows up as a nice bright spot. And they've actually designed some radiotherapy applications around this tracer and how specific it is. But we were just looking at it with a PET scanner. We also acquired some diffusion weighted imaging. And you can see the dark spot here. You get increased cellular density, so reduced diffusion in tumors, so we see a nice dark spot there. And then we also acquired some CSI, so 3D spectroscopy images, and we looked at the metallic ratios, and it was as we would have expected. Yes. But anyway, so that's enough about me and my past. Now I'm going to spend some time telling you about how to bring an MRI pulse sequence onto your scan. Why would you want to bring in a new sequence? You may be happy with the images you're getting, but the reality is that if you're using the default sequences that are on the scanner, you're probably not using the best sequences. It takes quite a bit of time for a sequence to be developed, and the ones that you're seeing on the scanner are the ones that have been tried, tested, and true for a long time, and they're always going to work, but they're not cutting edge. And the reality is that novelty gains papers, right? So if you have a cutting edge sequence that you're using, your results don't necessarily even have to be that amazing. I mean, you hope that they are, but it can definitely accommodate, it can definitely help you out with getting your paper published. But as soon as they see that you're using this cutting edge sequence, they're like, okay, well, this is interesting nonetheless, so let's get it out there. Sometimes it's very easy to get a new sequence to it. It's not nearly as hard as you would expect, and I'll explain that in a second. New sequences can provide better SNR, better contrast, more reliability, just generally better image quality. There's all different types of sequences you can get. And I've talked about this a few times to a few of you, but I'm a bit of a spectroscopy snob, so like if I'm reviewing a paper and I see that you've used the basic spectroscopy sequences, my immediate thought is that you don't know a lot about spectroscopy, and I'm going to be a little bit harder on you because I'm questioning the methodology. But if I see one of these new sequences that are very easy to get, then I know you've done your homework, and I'm willing to give you a little bit more leeway in that regard. I'm kind of a new reviewer in that respect. But so this is the pipeline for sequences that are coming out. You have an external research site. They develop their sequence and their protocol for it, and they present it in papers. They present it at conferences. You get a lot of buzz around it. People are requesting the sequence from them, and manufacturers like Siemens, they're going to hear about this buzz, and they're going to be like, okay, well, we want this sequence on our scanner. So they're going to assign a programmer to it. It's going to become the programmer's baby. And then the programmer is going to build up the sequence, and he's going to be working with customers, making sure the sequence works just fine, there's no issues, no bugs. And once it's at that point, it becomes a Siemens product. And that can take a long time to go from the first one to the last one. And so what you're getting on the scanner is the last one. And really, you have the most flexibility in the first two. And how do you get these sequences from these sites? One method is, it's called the C2P. I don't actually know what that stands for, customer to something, or I'm not actually sure. But it's people that have done the grunt work for you already. And pretty much all you have to do, you contact the external site and say, hey, are you willing to share that sequence? And if they say yes, you have to do some official paperwork with Siemens, then you can get it. It can be, sometimes it's that easy. Not always, but sometimes it's just a matter of a few emails and then we've got it. Another way is it's a WIP, so it's a work in progress package. So that's where the developer is, so we have the Siemens programmer. It's on its way to becoming a Siemens product, but they want people to be using it. So it may seem like it's in Siemens development, so it's like you gotta jump through a bunch of hoops to get it. But really, they're eager to have people working on it. They want feedback from different sites that are doing it, and these are going to be cutting edge sequences that you can get access to just with an email away. Occasionally, they may ask you to do something. They may ask you to try some scans, give a report on the results. Because they're not a product sequence, there's a chance they may be a little bit buggy, but they always, the basics of it seem to always work very well. But the main downside to going through it being a WIP is that it's eventually going to become a product sequence. And when it becomes a product sequence, then you have to pay for it. So all you got to do is contact Siemens, they'll give you the sequence, but you got to pay for it. And at this point, the sequence is going to work. Like, it's been tried with every parameter set that they're giving you, and it's going to work without any hitches. One problem is that if you want to go outside that parameter set, you can't do that. Whereas when you have the C2Ps or the WIPs, you probably could. And then the last option is to write it yourself. And this one is, it's more of a project. It can take quite a bit more time. There's a bit of a learning curve when it comes to pulse programming. But really, what all you got to do is just stick a lowly graduate student on it. That's me 10 years ago, and that was pulse programming. It is a sought-after research skill, so for a young researcher, it's a very good skill set to have, and they should be willing to jump on this opportunity to get familiar with the pulse programming environment. And once you have written your own code, you have full control over it. You can decide what parameters you want to play with, and it's a very good way to get your hands dirty with the MRI and to really understand how the MRI works. But and there are courses you can take that cost money, but they are helpful. So some examples of what we have here currently. One of them is the multi-echo NPRH. We got that through C2P with Harvard, I believe.
Yeah.
Okay. And how that works, it's essentially your typical NPRH you have on the system already, but you use a higher bandwidth to reduce some of the distortions through your imaging, and you require 4 echoes, and you bring them all together, and you don't lose any SNR, but you get better homogeneity in your images. So it's the same thing, it's the same scan time, it's just a better sequence. And it's just as easy as getting a CTP. Another one is the multiband epi. And how that works is it's like your epi sequence, but so echoplanar imaging sequence, so whatever you would use for fMRI. But what it's doing is it's using a fancy RF pulse to acquire multiple slices concurrently. So instead of acquiring one slice at a time, it's acquiring anywhere from 1 to 6 slices at a time, or 8. And that's having a direct effect on your repetition time. So if you think of it like you're doing functional, if you're doing an fMRI resting state scan, and you want to map out the time course, you are getting more points per unit of time because you can get a lower repetition time using the multiband epi. Another one is the MRS package, again through CTP. Both of these were through Minnesota. It's kind of what I showed you earlier. You get far superior data than what's available on the system with the basic press and steam sequences. And this one, it's honestly, they get so many requests for this that it's as easy as going to their website, downloading the C2P, signing it, and sending it back. And then you get all these state-of-the-art sequences. So very, very easy to get these sometimes. Sometimes it's a little harder than others. But, and then we also have a work in progress package with the Ute sequence. So we have the code I've modified it so that it's that we can do full body scanning with it instead of just the skull. And Gerd and I are also working on a custom T1 row sequence. So we got a sequence that was similar, and we're just going to add some RF pulses, and then we have our own sequence that we can do whatever we want with. And this, I just am showing this because I wanted to, let's see if I can get this post, yeah. Just show you like all the different things that you can get So the basic SNEAM sequence, it has normal RF pulses here. Okay? This one that comes in that spectroscopy package, they have fancy RF pulses. So it allows you to get echo time way shorter just from that tiny modification. The basic SNEAM sequence has 3 water suppression pulses. This one has 8, and you can actually optimize all of them individually. It has outer volume suppression to clean up your spectra, which the basic sequence doesn't have. And it has this additional water suppression pulse. So just to show you how more superior some of these sequences can be. And like I said, this one was very easy to get. So just quickly, I'm going to go through the steps that we would take to get the sequence onto the scanner. First of all, you got to find the sequence. You read it in journal articles. You see that people are using this fancy new sequence. It could be a paper on the sequence itself, or it could be someone else that's done an application using the sequence. So sometimes you could contact the people that wrote the paper and say, hey, where did you get that sequence? And you can get in contact with the person that wrote it, and you can see if you can bring it over. One of the best resources, this conference here is one I go to every year. It's the International Society for Magnetic Resonance Medicine. There are whole sections dedicated to the pulse sequences that are coming out. And they're always eager to have people using their sequence because they want to get it out there. They want feedback. They want to know how they can improve it. If you don't know, if you've read the journal articles, you can't get to the conference, you can just contact the Siemens representative, so our local representative, Jerry Moran. You just ask him, okay, we want to do this study. Do you have any recommendations? And he's a very knowledgeable guy. He knows what's going on, and he could. Sometimes he'll say, I know this person does this, why don't you ask this person? So he may not have the final answer for you, but point you in the right direction. And then there's me, 10 years ago. But I can also, I may not have an answer for you, but...
Your attention, please. A volunteer contribution on the main floor is
so
now open.
Then you turn the system. So when I was Googling image for V11P, I couldn't find anything. But I did find the V11 Thunderseeker. Unfortunately, we're not at schools that have a system that's V11 Thunderseeker. We're on V11P. But that's the software line. The P stands for PET, so PET MRI. So we are very specific. Like we have this here, and only PET MRI is going to have this. But if you want to convert a sequence from V11A, B, or C, which most scanners will have now, it's typically very easy. There's other software lines that might be a little bit more difficult, like your project that you can definitely be done. Then you contact the developer to say, are they willing to share the sequence? We're willing to share the executables, so that's when they compile it for you. So they would have to compile it on V11P and send it to you after you've done the official paperwork, and then you put it on a scanner, and that's it. Sometimes if they don't have it on V11P, they may send the source code, so the programming code, where we would take the code, compile it here, and then give it to, so they'd actually like that, because then they get a copy of the V11P software that they can distribute later on. So that's another option, but they're often very protective of source code as well, so you don't always get it. But yeah, you discuss how you can get it on your system with V11P. Then you contact Siemens, and I know it's kind of a nuisance sometimes to contact Siemens and say, hey, we got this, they're willing to give it to us, what paperwork do we have to do? Sometimes it takes a couple of weeks. They're fairly efficient with it still, but it can really be a nuisance. But it's a good nuisance because developers are a lot more keen to give you their sequence when they know they're protected from all this paperwork. So this would be something that you would contact Jerry. You would say, hey, you know what, C2P or a whip with this site, and he would take care of it for you. Sign some papers, and that's that. And then they give you the source code, put it on the scanner, and that's it. So yeah, that's pretty much how you bring the sequence on there. But just to summarize, there's almost always, I've said this a ton of times now, there's almost always a better sequence than the default on the system. 9 times out of 10, if you're using a sequence on the system, you could be using a better sequence. It's not necessarily hard to get. Sometimes it's just a few emails away. There's lots of ways you can do it. You can sometimes, even if it comes down to it, so if there's a will, there's a way. If you really want the sequence, stick a program, a grad student on it, and let them work on it for a year or two if you have that time. But then the sequence is yours. And finally, don't be afraid to ask. Like I said, I'm a resource to you guys. My role has some pulse programming implications, so I'm happy to help. I actually like doing pulse programming, so yeah, any opportunity that I get for it, I'll probably jump on it. But yeah, so if you have any questions, feel free to ask now or you can email me later. That's it.
So on your 70 images that you worked on before, it seems that you were easily separating glutamine and glutamate. Can we do that here as well?
Not as much, no. So it's kind of like a physical, like a law of physics, right? The higher field strength you go, the more separation you're going to have between the two. And as they come together, so as you get a lower field strength, they're going to come together a lot more. And it's just, it's based on let's see if I can find which slide that was. How that works is the scale that you're looking at, it's a PPM scale. And parts per million, the number of hertz per part per million is going to change as you change field strength, right? So I don't have the scale there, as you can see where I've removed it. There's a little line in there. But so one of these would be 1 part per million. 17, that represents about 300 hertz. So the separation between glutamate and glutamine, maybe 20, 30 hertz. But then you go down in field strength, that's 1 ppm to 3T, that's 128 hertz. So they are still like a little bit separated, but they're going to be kind of, there's going to be a little bump just on the side where glutamine is. Some people claim to be able to separate it, but it's, and you can try. I mean, you can pretty much, whenever you do a spectroscopy study at 3T, it makes sense to report glutamate and glutamine individually, and then also report them together as GLX is what we call it. Mm-hmm. So yeah, you can do both, and then you can extract conclusions from that. You also say that yes, at 3T it's harder to differentiate the two, but
You know how we did testing with you? I don't know whenever that was. Were we using the same?
Dr. Rogers.
That's something you
Dr. Rogers.
yeah, we're using
We're
using, which one was that? It was one from the software package that we got, yeah.
So we're using Press.
Press, yes. We're using the Press sequence from Minnesota. Yeah.
So Kurt and I have looked at the glutamate peak, and yeah, it's kind of as you say, Reggie. Like sometimes it seems like we have two distinct peaks, and then the next time I scan myself yet again, we don't. So
right.
I would say it's not particularly reliable.
Yeah.
So it's not you personally?
Well, I don't know. I don't know yet.
Maybe you're not very reliable sometimes. That's what I see.
Like if you had really good shims, you probably could. So if you were looking at an area like the thalamus where there's lots of iron, you're probably not going to get good shims, and you probably couldn't differentiate glutamate. If you're looking at somewhere on the external part of the brain, you can probably get a good shim there, and that's going to change your line width. So you might be able to see, you might be able to differentiate them.
What about simpler things, like just tweaking existing sequences? Like they're packaged and they're sort of locked down and
so yeah, that's actually a really good question.
Possible to just develop on what's already available? To sort of say, well, I want this, I like this sequence, but I have some ideas about improving it.
Yep.
These things are possible.
So yeah, actually, I should have included that. I'm glad you asked that. So what you can do is you would, in that case, you would talk to Jerry, the Siemens guy, and you would say exactly that. And it would be like through me, because I would probably be the one working on it. But if you approach them with a project and say, hey, we want to do this using the existing sequence, but given what's on the system, we can't do it. Would you be willing to share the source code with that sequence so that we can modify it in the system? Sometimes they might say no, but they definitely said yes in the past. That's kind of how we got the unique sequence. So we just said, we can't get a big enough field of view, and give us the sequence.
Yeah, it makes sense. Like they've done like 90% of the work for you.
Yeah. It's sometimes it's just as easy as changing the parameter set. There's sections of the code. There's one section that has all the parameters. You can just change it there. It would largely depend on the research agreement that the site has with students, but I think it should be.
So now, what about the pitfalls or limitations or drawbacks of using these sort of untested or less tested sequences?
Pitfalls and drawbacks. Well, like the big one, like I said, was that they eventually product and eventually have to pay for them. But pitfalls, I mean, yeah, there is trust, but like typically these sequences have been published. They've been scrutinized heavily. Other people have been working on them, and like that's one of the things is that it is a trust thing, and they want feedback. But for example, this Minnesota group, like that sequence is not going to be bad. So many people use that. They have a full team dedicated to that. It's really their sequence is it's going to be described in the paper. You read the paper, and then if there's any limitations from that sequence, it'll be in there. There's not a whole lot of... the thing about Siemens, when you're programming with Siemens, is that everything has to be perfect. Like, your timing has to be perfect, your estimation of the SAR values has to be perfect. All that has to be perfect. Otherwise, it'll give you errors in a compile. So, unlike other environments, like when I was using Varian, I could just throw an RF pulse in there, and it may be giving me the wrong data, but it's not telling me, right? So even like the echo, it measures the echo. Is it exact? No. Well, then throw it in there. So if it's passing all the errors, it's probably a good sequence.
So it's lots of checks and balances.
Yeah. There's something called a unit test that checks it pretty good.
Reggie, so for our MRIs, when we're doing the shimmy with the fast map, and then you threw in something else last night.
Yeah.
Could you explain that? Because sorry, we were kind of rushed and I didn't quite know
yeah.
and I was looking at my notes and I'm like, I don't know what we did.
So
that's a terrible question because I haven't really asked a question, but perhaps.
No, that's a good question.
Explain that.
So I'm going to use this one. This is the steam, but it also has the same water suppression module that we're using. It has different flip angles. So this is a 90 degree, and then in steam it's 390 degrees, but in press it's 90, 180, 180. And so that's, I put in 3 optimization steps, which we reduced to 2. But the one that you definitely want to do, and these are things that are built into this sequence that are not normally built into a sequence file on the system. So they built it in, they put their own pulse programming to do that. So, and it makes it way better. It was the power of the RF pulse for the vapor water suppression. And so what you do is you give it a range of flip angles. So you start at this flip angle, range to 50 degrees out with every 5-10 degrees increments, and then it'll pop up on the screen and it'll show you the decrease in water, and then you select whether you're happy with the amount of water that's been suppressed. The other 2 that I did was the 90 degree that was here, and then the 180 is there. Ideally, you would do both, but because there were two 180s and 180s are a little bit more sensitive, we decided to go with the 180s. That was what we optimized that time.
So that's sort of a user interface. So you guys kind of decide when, like, the optimal point in that curve where you're like, no, that seems fine. We're probably not going to gain much more by.
Yep, exactly. There are a lot of other things that, I mean, you could spend a half hour on
Right,
and
right.
stuff. And your spectra will look amazing, but that's not the main point of your study. And it's some point you have to compromise.
Yeah.
Any other questions? You can always email me later if you have anything or think something later. Reggie Taylor.
Alright, should we adjourn then to our users meeting? Those of you who want to stay